Okay, welcome back. So before I go on, I should mention that the previous exercises, which involve truth tables and constructing truth tables from these logic gates, these will be important in the future because I'll be using truth tables for the rest of the lecture. So if you haven't done the exercises, I would strongly recommend taking a look at them, trying them out. There's not too many of them, and they should be pretty straightforward. I've given you sort of the model of how to do one of them, I think the NOT gate, and so the other ones are kind of similar. Okay, but assuming you've looked at the exercises, now I'm going to talk about combining gates. Right, so before we defined gates in isolation, there was a single AND gate or a single OR gate or an exclusive OR or something like that. But in practice, when you build a processor, when you build up a computer, you use multiple gates in tandem and you build all kinds of complicated circuits with them. So let's talk about the basics of how you do that in some simple examples to begin with. Okay, so we know what an AND gate is. We know what a NOT gate is. So now we're going to build something called a NAND gate. Okay, so a NAND gate is another gate. It looks like this, right? So it looks similar to an AND gate. It's the same shape, except that we add a little circle on the end, which is the same circle that shows up in the definition of the NOT gate and its visual depiction. So what does a NAND gate do? Well, a NAND gate, N AND is really short for not AND. So what this does is, it takes two inputs and it spits out one input. And in particular, it takes those first two inputs, puts them through an AND gate, feeds the result of that AND gate into a NOT gate, and then outputs the result. So a NOT and an AND gate put together in this order gives you a NAND gate by definition. Okay, so let's look at, in particular examples what happens. Right? There's only 4 cases, so we can work them all out. So if I put in a 0 and a 0 into a NAND gate, what happens? Well, the 0 and 0 go into the AND gate, and then they spit out a 0, because, an AND gate takes in 2 zeros and spits out 1 0, by definition. And now I pass that 0 along this wire into my NOT gates. But now the NOT gate takes the 0 as input, and it flips it, and it spits out a 1. So at the end of this process, 2 zeros should give me a 1. Okay. Similarly, if I put in a 0 and a 1, right, the exact same thing basically happens. 0 and 1 goes through, I get a 0, and then I flip it, and I get a 1. So this is the second case. In the third case, I put in a 1 and a 0, and I spit out a 1. Right? This is pretty much identical to this case because it doesn't matter if you flip around the 1 and the 0, the same thing happens in the AND gate. It goes to 0. So the last example is when I give it a 1 and a 1. And this is the only different one, in the sense that 1 and 1 put through an AND gate gives you a 1. But then if you pass that 1 through a NOT gate, it flips it and it gives you a 0. Okay, so let's think about this in terms of the truth tables that we were just working with. So the truth table for AND, right, 0 and 0 gives you a 0, 0, 1 gives you a 0, 1, 0 gives you a 0, and 1, 1 gives you a 1. This is what AND looks like. But I think it's important for all of these gates that we look at their truth tables. So let's try to build the truth table for NAND. So this is kind of easy in this case because all you need to do is you just take the output and you flip it, right? Because that's exactly what happens with these AND gates going into these NOT gates. That's how you get a NAND gate. So 0, 0, 0, 1 in this right column goes to 1, 1, 1, 0. I've just flipped each output bit. Okay, so this is the definition of the NAND gate. It's a relatively simple way to take two gates and put them together and get a slightly more complicated gate, which might be useful when you're building a circuit. So there's one more thing I should mention, which is that I can define a similar thing called a NOR gate and an XNOR gate. Right, so recall that the 3 basic gates that I defined, besides the NOT gate, were the AND, OR, and exclusive OR. So correspondingly, I have a NAND, a NOR, and an exclusive NOR. So I'll leave it to you to guess how you define these things. And the hint is that, well, it's basically the exact same way as you define this thing. You just replace this AND gate with the other two. But at this point, I would encourage you to pause the video and write down what you think a NOR gate is and try to compute its truth table. And write down what an XNOR is and try to compute its truth table. Okay, so let's move on. So let's try to do something slightly more complicated. Instead of just combining two gates to get a brand new one, I want to make a gate that I already know how to build. And I want to build it using other gates that I know how to build. Or that I just, take for granted. So I can start with NAND gates. So, say I'm an engineer and I'm in a lab and I just have a bunch of NAND gates. And I'm supposed to build a bunch of circuits. Well, I might think at first, okay, I can't do any of this because I don't have any of the other gates that I want. But then I can say, well, maybe I can build some other gates. So the first one I try is the simplest one, which is the NOT gate. Okay, so I'll tell you how to do this one. This is kind of a basic example. So let's say I have a NAND gate, right? I put a NAND gate in the middle because that's all I have, essentially. Okay, now I can feed as an input to this some input, right? I mean, I want to make a NOT gate. So a NOT gate in particular has one input and it has one output. But a NAND gate has two inputs. So the only sensible thing to do is take the input that I'm given and feed it into this NAND gate, but feed it into both ports of the NAND gate, right? So in particular, if I feed it a 1, if I turn this input wire on, then it splits this into two wires which are still both on, and these wires go into a NAND gate, right? So it's a 1 and a 1 going into this gate. But we looked at by what we understood from the truth table before, this should output a 0. Right, so 1 and 1 go to 0, and then this wire is then off, and so the light bulb at the end of the circuit does not turn on because this wire is not charged. Well, in this schematic at least. Similarly, if I put a 0 into the same exact thing, well, now I'm giving a 0 and a 0 into this NAND gate. But if we look at the truth table from before, a 0 and a 0 going into a NAND gate give us a 1. So this output wire is now charged, and the light bulb turns on. Okay, but now if you look at what's happening, I'm putting in a 1 and I'm getting out a 0, and I'm putting in a 0 and I'm getting out a 1. And this is exactly what happens when you build a NOT gate, right? A NOT gate is exactly defined so that when you give a 0 or a 1, it flips it and gives you the other one. So this is great because we now have successfully taken, one of our primitive gates that we defined, and we've built another one. And all we had to do, really, for this example was just use one of them. And I guess for this example, it's maybe not so surprising because there's already a NOT gate sort of in the definition of a NAND gate. So maybe it's not so surprising that you can do this. So let's think about another example. So in this second, more complicated example, I want to start, say I'm the same engineer, but now instead of having a NAND gate, I have an AND gate and I have a NOT gate. And from these two gates, I want to build an OR gate. Okay. So, this is kind of nice. I have, OR is something that takes in two inputs and has one output. But that's fine because an AND gate is also something that has two inputs and gives one output. So I'm at least sort of, it's at least sort of plausible that this kind of thing could work. So let's try it out. So instead of just directly building the circuit like we did before, why don't we try to look at the truth table and see if there's some sort of way we can simplify this and make it a bit more conceptually clear how we actually do this. So first we'll write out the truth table for an OR. Right? For an OR, you have 0, 1, 1, 1 in the truth table in the output column. Okay. So the first thing we can do, well, we have a bunch of NOT gates. And so we can try to just, build some circuit, it's like I want to build a circuit that behaves like this. But I have a NOT gate, so I can negate whatever output I get. And so if I want to build a circuit that does this, all I need is a circuit that does this. Because I can take this circuit and then I can just stick a NOT gate at the end, and then I'll get this circuit. So really, if I want to build this, I just have to find something that realizes this. Right, so now the truth table looks like 1, 0, 0, 0. which is nice because this, as this comment says above, looks like an AND except it's upside down. Right? What do I mean by that? If you look at the truth table for an AND gate, it's 0, 0, 0, 1. Okay, but this is kind of different, right? Because, I mean, it is sort of 0, 0, 0, 1, but in the other direction. Okay, so this looks like a problem. But now let's think again. We have NOT gates at our disposal, so we can keep playing around with these NOT gates. And if you want to flip this table upside down, well, one thing you can do is you can just flip all of these inputs. Right? If I flip the 0 and 0 to a 1, 1, if I switch these two around by flipping 0, 1 to 1, 0, and vice versa, and I flip the 1 to a 0 and I flip this 1 to a 0, then the whole table suddenly turns upside down. So if you think about it, really what I'm doing is I'm taking my input wires and I'm applying NOT gates to them. So now I'm going to flip the input and I get a table that looks like this. Okay, but by our convention, this is not what a truth table looks like, because a truth table should, it should have this order for the inputs. So now we just rearrange our truth table so that it looks like what we're used to. But now if you look at this is exactly the truth table for an AND gate. And an AND gate is something that we're allowed to use. Okay, so now we sort of have a conceptual roadmap of how to build the circuit that we want, which works as an OR gate. So below I'm going to sort of draw how you go back, starting with this AND gate that you now know that you need to start with, and add all of the NOT gates and get back to the OR gate. Okay, so this AND gate realizes this truth table, right, by definition. And if we go one step further, well, this truth table is just a rearranged version of this truth table. So still an AND gate will realize this truth table, right? Okay, but now let's move on. So now I've flipped the inputs conceptually. So what that means is that to this AND gate, I'm not just giving it the raw inputs that I, give to my computer, or give to my circuit rather. I'm first flipping them using these NOT gates, and then I'm inputting them into my AND gate. Okay, so this is a circuit that will actually realize this truth table. If you just go through the process and follow all the steps, this is what you get. So lastly, here I flip the inputs. So I put NOT gates before the AND gate. But then the first step, in analyzing this truth table was to flip the output bits. Or in other words, apply a NOT gate to whatever I get from this AND gate. So I tack on this extra NOT gate at the end. Okay, so now here is a circuit which realizes this truth table. So I would encourage you now to pause the video and look at the circuit, maybe draw it on a piece of paper and play around with it. And just sort of look at what happens when you put in a 1 here and a 0 here, or a 1 here and a 1 here, and trace through this thing, look at each step, and convince yourself that this thing actually does realize this truth table. Okay. Okay, so this is a slightly more complicated example, which illustrates how you can, take 2 or more different kinds of gates and create another one that you already know how to make. Okay, so now it's your turn. So there are now more exercises having to do with, taking gates that you already have and then trying to build one that you already know about. So for the next part, I encourage you to look at all the exercises, try to do as many of them as you can. Some are easier than others, but just go through them and try to have fun with them. And I'll see you for the next video.